In the name of the Almighty, the Compassionate, the Merciful. Again, here now, we are going to study differentiation. In other words, we reached the end of the road. This is the subject actually we are concerned with because the science is called what? Differential and integral calculus. And this is actually the first part of it, which is differentiation. But in fact, we could not study differentiation without making resort first, furnish first basis to differentiation. The basis is, first of all, you have to study limit, and we did it, as well as we have to make sure that the function is continuous. Otherwise, you cannot differentiate a function. In fact, most students can very well differentiate a function. Like, for example, if they wish to obtain the derivative of x cubed, they say it's equal to 3x squared. This is simple, but the problem is not really to differentiate whether simple or complicated functions, but the idea to understand what's the meaning of differentiation. The derivative, as a matter of fact, have different terminology in literature. As we said, and we said this before, engineers use the word terminology slope of tangent. Like they say, for example, this ramp or this road, what is the slope of this road? Physicists, on the contrary, they use the word rate of change. And all these two terminologies, as a matter of fact, are equivalent to the word derivative. In this lesson, we are going to discuss the following issues. First, we are going to define the meaning of a derivative, and then we are going to speak of we are going to speak about differentiability in intervals, and then the laws of differentiation, and then the derivative of elementary functions, and then differentials. These are the topics we are concerned with now. First, we come to the definition of a derivative. If you, for example, have a relation of this sort, y is equal to 3x. Suppose y represent the temperature and x represent the time. So what you say here, we say that y increases 3 degrees every second. If x is equal to x1, after 1 second, the temperature is 3. Whereas when x becomes 2 seconds, you get 6, 3, 9, etc. So in fact, you have what we call a linear relation. It increases linearly. In other words, it doubles every second. 3, then 6, then 9. If you wish to calculate the rate of change of this function, that is the rate at which it increases, all you have to do is that you divide two different values of y by two different values of t, and then you get the rate. This is the rate. For example, here is 3 and here is 6. So 6 minus 3 divided by 1, you get 3, or 9 minus 6 divided by 1 again, which is the interval of time at which it increased from 6 to 9, and you get 3. So actually here, this 3 represents the rate of change of this function, and in this situation, it's a constant. It does not jump from a rate to another rate. The rate here is constant. In other words, it proves it increases at a constant rate. But suppose this is not the case all the time. Suppose we have, for example, a situation in which, for example, we have a falling body under gravitation from the top of a cliff, for example. And this, if you want to represent the velocity, it's equal to g, the gravitational constant, times t, whereas the distance which the body traveled is equal to half gt squared. And this here you realize something. You realize that after 1 second, the distance traveled is equal to 0.5 g. Whereas or we better have another slide here. After 1 second, the velocity becomes equals to g, and starts from 0. And then after 2 seconds, what happened is that it reaches 2g. And here is the velocity g. So actually, after 1 second, if you notice the difference between the velocity and the distance which the body had traveled, you realize that after 1 second, it had traveled half g. So actually, the distance is equal to half g. Whereas after 2 seconds, it had traveled 2g. So actually 2g minus half g, it has traveled 1.5 g. So this is the distance after, in the second, it has traveled 1.5 g. And in the first second, it has traveled only half g. As to if you leave it another second also, in other words, after 3 seconds, it has traveled, in fact, you substitute t is equal to 2 in half gt square. You find it equal to 4 is equal to 2j. This is after 2 seconds. This is the first second, 2 seconds. As after 3 seconds, you substitute 3, you get 4.5 minus 2, you get 2.5j. So actually, what happened is that although the velocity has increased linearly, it was after 1 second it became g, after 2 seconds 2g, after 3 second 3g. You find that the distance have the behavior of distance is different. It has actually traveled half j in the first second, and then 1.5j, and then 2.5j. So this is the distance that the body has traveled. And you find out that the rate of change of the velocity is constant. It increases at a constant rate. The rate here is what is j, because it's j, then twice j, then 3 times j, etc. So you can actually have a relation like this of slope equal to j. This is the slope. The tangent of this angle is j. Whereas for the distance, it has actually been it has been behaving like a quadratic function of t. It has traveled half a j, then 1.5j, then 2.5j. The velocity, the mean velocity, these are equals in fact to the mean velocity. Even the mean velocity of the first second is half j, the second velocity is 1.5, the third is 2.5j. Because here, for example, in the first second, it started from 0 to j, so 0 plus j over 2, it gives half j. Here it has ended after the first second by j, and then the second by 2j, you get 3j, j plus 2j, 3j over 2, you get 1.5j, and here is 2 plus 3, 5 over 2, you get 2.5j. So in fact, this body has traveled at a rate which is not linear. It is a linear with respect to the velocity, but is not linear with respect to the distance. If you wish to calculate, for example, here it is. The first distance is half j, the second is 1.5j, and the third distance is 2.5j. You see, it increases at a faster rate, the distance at a faster rate, whereas the velocity at a linear rate. So now, if you want to calculate the average velocity in the interval from t to t plus 1, at any value of t, at any instant of time t, what happened after 1 second? And you wish to calculate the difference of y by the difference of x. This is as like in the previous example, difference between two values of y divided by difference between two values of x. So after t plus 1, it had traveled this distance, minus the value which has traveled after t. The difference between the two is the distance which traveled between in the interval from t to t plus 1. If you divide it by 1 second, you get a relation of this. This relation tells you what? Tells you that the rate at which, or the average velocity in the interval between t and t plus 1, the velocity is about 0.5 g plus gt. As in fact, this very well conform with our previous results, because when t is 0, you get half j. When t is 1, you get 1.5 g, etc. So now, if you are speaking about, now you are, in this example, we take elapses of 1 second. After we watch out for the behavior of whether the velocity or the distance after every second, after the first second, then after the second, then after the third second. Suppose we wish to calculate this average in a very small interval of time, because 1 second actually is large. So what we do, we take an interval of between t and t plus delta t. This delta t is a quantity. In fact, students think that this is small. No, it may be large. It may be a difference between two cities. But what is important at the end in that we take this limit here when delta t approaches 0, and this is the idea of the limit. And the differentiation, in fact, what you do, this is the average velocity in the interval between t and delta t. You divide it by delta t and you get the average velocity. If you take the limit when delta t tends to 0, you get Vt. And what is Gt? The G, in fact, represent what? The limit of delta y by delta t when delta t tends to 0. So this, in fact, in this case only, that you got what you call the instantaneous velocity at the point t, because we see that t increased linearly. and the distance increase in quadratic form, but the rate of change of the velocity is constant, whereas the rate of change of the distance gives you the velocity at that particular instant of time, because in fact the velocity changes. So the velocity it's the rate of change of the distance, and it's always given in the form of gt. In fact, this equation or this expression was known before at the time of Newton and Leibniz. It's not new. The only difference is when Cauchy comes and intervenes here with the idea of limit. When you take the limit, you obtain gt, which is the instantaneous velocity. So the instantaneous velocity, if y represent the distance and t is time, the instantaneous velocity becomes equal to gt. In other words, you take the limit of delta y by delta t. And if it exists, then we say that the function y is differentiable at the point t. What we do, in fact, concerning now, we return now to the case where we are concerned with a function f defined for over an interval, and we wish to obtain the derivative at the point A. What we do is the following. We subtract two values of f at different at A and x, and which is away from A by a distance h. In other words, x is equal to A plus h. What we do is that we take a secant here. At the point A, we construct f of A. This is the green pointed line here. And then another point A, which is away by a distance h, we construct another f of x here, and then we connect these two by a straight line. This is the secant, and what we do is that we move the secant until it becomes it touches, it becomes a tangent to the curve at the point A. If this is so in fact what we do is that we subtract two values of f at x and a, and you divide by x minus a, the difference between these 2 points, to obtain, and we take the limit, we obtain the derivative at the point A. Or we can use this similar expression here. Actually, both are equivalent. What in fact you do is the following, is that you have a point, for example, this point, you wish to calculate the tangent at this point, the slope of the tangent. This is the derivative at this point. What you do is that you take, you move another point which differs from the x of this point by a certain amount, delta x. And you keep approaching between, you let this point here approach the point at which you wish to calculate the derivative. So actually here you see that this is delta x positive and delta y is positive. And you divide delta y by delta x. When you divide delta y by delta x, you get the slope of the secant. But when this point, which changes over the curve, approaches the point at which you wish to calculate the derivative, then in this case only you get the derivative at this point, the slope of the tangent at this point. And in fact, this is the limit. The limit of delta y by delta x when delta x approaches 0. Of course, when delta h tends to 0, delta y, of course, also tends to 0. And the quotient in this case, where both tend simultaneously to 0, become equal to what we call dy by dx, or the tangent, the slope of the tangent at the point at which we wish to calculate the derivative. Suppose, for example, we move the point to the other situation here. The same thing. We have here a secant. This is actually the slope of the secant. You see that it has as the slope, the tangent of this angle here is equal to delta y by delta x. And because delta y in this case it's negative, and delta y and delta x could be positive or the contrary, then here, for example, here delta x is positive and delta y is negative, and this is why you get a slope which is negative. And once both approach each other, the secant approaches, in other words, this point which is moving, approach the point at which you wish to calculate the derivative, then only you get in the limit the derivative of the function at the point, at the red point here. For example, calculate the derivative, this is an example of x squared at the point x is equal to 1. Then we use either expression. Here, what we do is that we have the function f, you have x is equal to x squared, and you wish to calculate the derivative at the point x is equal to 1. So the derivative becomes the limit when x tends to 1 to what? To x square minus the value at x is equal to 1, which is 1, divided by x minus 1. This is the derivative, in fact, at the point x is equal to 1. When you calculate this limit, you decompose the numerator, you obtain here the limit when x tends to 1 plus x plus 1, and you get 2. In fact, what you do here is that you are calculating the limit of another function, not this function x squared, but the function x squared minus 1. In other words, suppose, for example, we wish to draw the graph of this function, which is x squared minus 1 divided by x minus 1. It is what? It is actually something of this sort here. This is the point 1, and which you wish to calculate the limit. And this is the limit which is equal to 2. And this is the point 1. This what? You wish to calculate the limit of this function at the point 1. And this function is not defined at the point 1, but it has limit equal to 2. And this graph is in fact drawn for what? For the point A equal to 1. Suppose now that you wish to do the same thing at another point. 2, for example. So you calculate the limit of x squared minus 4 divided by x minus 2. In other words, you draw another graph, x squared minus 4 divided by x minus 2. This graph, it tells you that at the point x is equal to 2, again, it's undefined. And then this is the case at a is equal to 2. And you wish to calculate the limit at x equal to 2. At a is equal to 2. So what you get here, you get 4. So in fact, what you do is that for each particular point at which you wish to calculate the limit, you have a different graph of another function which is not defined at the point at which you wish to calculate the derivative. But when you connect these lines together, you get y. You get y is equal to 2x. And y is equal to 2x is the general derivative at any point x, whether it is 1, 2, etc. And this is, in fact, what you get. And therefore, the idea actually is the limit. You have to remember something, that you cannot calculate the derivative of function unless the function is continuous. For example, x squared is continuous at the point 1 and 2, etc. Its domain is R and it's continuous on R. And therefore, we can calculate the derivative. If the function is not continuous, then you cannot calculate the derivative. And this is what is stated in this theorem. The theorem tells you that if a function is differentiable at point, then it is continuous at that point. And this is easy to be proved. All you write to do, you write f of x minus a, and you divide by x minus a. And since the limit of a product is equal to the product of the limits, provided that each exists, this one is what? This one is the derivative. And if it exists, then you got f dash prime, f dash of a, whereas here, when x tends to a of x minus a, you get 0, and therefore this limit is 0. It means that limit f of x when x tends to a is equal to f of a. In other words, the function is continuous at a. So in fact, if a differentiable function at the point is continuous at that point, but the contrary is not true. It may be continuous, but not differentiable. And this is why if you meet a function which is not continuous at the point, there is no need to calculate the derivative. All your effort will be in vain because there is no such a derivative. Usually instructors, in order to exemplify this theorem, they take an example in which the function is continuous, but it's not differentiable. Of course, the opposite is true according to this theorem. But whether it exists a function which is continuous and not differentiable, they usually give the example of mod x. Mod x is a function which is continuous everywhere. It's also continuous at the point x equals 0, but it's not differentiable at this point. How? Very simply, they take the limit of what? Limit f dash of 0, limit of what? F of x plus h minus f of h. This is the expression we used. F of 0 plus h at the point 0 minus f of 0 at h. And then they end up with this expression here. And this limit does not exist. And we said this before. The limit of mod h over h when h tends to 0 does not exist. Why? Because it tends to 1 from the left-hand side and to minus 1. In fact, the graph here is given as a function of h. It's different than this graph. I mean, this graph is the derivative of the functions everywhere on R. But the graph that we drew here on the paper is the graph of mod h over h. And mod h over h here does not have a limit at the point 0. It approaches 1 and minus 1, and therefore it has no limit. Suppose now that you wish to do the same thing at any other point. for example, at any other point, which is x, for example, greater than 0. All you have to do is that to take the limit of f of x plus h minus f of x divided by h, and take the limit when h tends to 0. In other words, in our case, mod x plus h minus mod x over h. Of course, if x is 0, then you end up with the previous graph with respect to h. But if x is positive, suppose x is 3, for example, and h is 2. You add 5 minus 3, 2 by 2, you get 1. So in other words, you have something like this. Suppose h is 3 also, but h is minus 2. So you end up with what? With also 1. So as a matter of fact, although this function is not defined at the word 0, at x equals 0, but it has a derivative at x equals 0. Why? Because it has a limit. This limit is equal to 1. So it tells you when x is positive, the derivative at any point x is equal to 1, and when x is negative, the derivative at any point is also equal to minus 1, because as you see here, this function has a limit at 0, and this function also. And also it has a limit when x is negative at the point x equal at h equals 0. So in fact, you draw the difference of f by the difference of x, and you draw it for different values of h, and you discover directly that the derivative exists whether x is positive or negative, but it doesn't exist for x equals 0. In other words, when x equals 0, you get mod h over h, which does not exist. If you add up all these derivatives at 0 and x positive and x negative, you end up with this situation, with this graph, meaning that the function is differentiable at any value of x, with the exception of x equal to 0. Therefore, now we have this theorem. Here what we have done is that actually we try to obtain f prime positive. In other words, we take the limit of the difference in y over difference x, when x tends to a from the right hand side, and we saw that if it equals to the rate to the same limit when x tends to a from the left hand side, if it exists, if they both are equal, then actually the limit exists of delta y of delta x, and we said that the function is differentiable in x. So in fact, what we did, provided that both limit exist, we say that the function is differentiable at the point a. So a function f has a derivative f prime at a if and only if the right hand derivative at a is equal to the left hand derivative at a. And this actually does not apply for the case when x equals 0 for the function f is equal to mod x, yet it applies for any other x which is not 0, either positive or negative. Suppose we wish to calculate the limit, not in this crude sense. We wish to calculate the derivative of mod x at any point x, which is not 0. What can we do? We do it in this brief case. In other words, we want to calculate or to determine a closed formula which applies valid for any value of x. So actually we work from first principle. F prime of x is equal to the limit when h tends to 0 to mod x plus h, though the same formula we used it before, minus mod x plus h, and then this is simple algebra. We multiply by the conjugate, and you subtract terms of x square, and you divide by h. Here you have 2h, and you end up with what? Mod x over mod x, or mod x over x when x is not equal to 0. So actually this what represents the derivative of mod x at any value of x. It's equal also to always to mod x over x, or x over mod x, with the exception of x equal to 0. So this function is differentiable except at x equal to 0. Usually mathematician tries to, they know very well now that function may be continuous but not differentiable. So they try to track all types of continuities, but at which the function is not differentiable at these points of continuities. And they could trace, in fact, three cases. The first case, which is called corner point, this is the one that we have just encountered, the one which you have mod x. Mod x here is differentiable with the exception of x equals 0. It is equal to 1 here and minus 1 here, and here it is not differentiable. And this is called a corner point because it changed sign, the derivative changed size from minus 1 to 1. Here we call this a cusp. A cusp is the point which is very thin, like a pin, for example, and you have a function like this, you see directly that the derivative here changes from minus infinity to plus infinity. And it's not differentiable again at the point x equal to 0. Here it is neither also, it is neither differentiable at the point x equal to 0, but the derivative, it tends to plus infinity and also to from the right or left hand side. We call this a vertical tangent. So actually you have three situations in which the function may be continuous but having no derivative at a point, like corner point or cusp or vertical tangent. Usually the student, and this is actually a common mistake, the student wishing to finding the derivative at a point, what they do is, like for example x cube. They wish to calculate the derivative at x is equal to 1. So they start first by calculate the derivative, and then they substitute x is equal to 1. Yes, in this situation, a simple situation like this applies, but in some situation it doesn't. Why? Because since you wish to calculate f prime at the point a, by, for example, by equating it to the limit of f prime of x when x tends to a. In other words, you wish to calculate the derivative at a point from the general derivative at any point, at any other point x, and then you take the limit when x tends to a. Is this true? Can you do this to obtain the derivative at a? No, you cannot do this. Why? Simply because this has to be true first. But this is not true unless f prime is continuous at a. And actually this can be exemplified here by this example. This example is not continuous at the point x equal to 0. Therefore, we conclude that it is not differentiable at x equal to 0. But does f prime exist anywhere? Yes, indeed, f prime here of x, the derivative when x is positive, you find it equal to 1. The slope is equal to 1. When x is greater than 0. It is also equal to, here it's equal to 1 also when x is less than 0. So in fact, although the derivative of the function does not exist at the point x equal to 0, the limit of f prime exists at x equal to 0. In other words, limit f prime limit f prime of x when x tends to 0 exists, is equal to 1. Yet the limit from the right hand side exists equal to 1, and the limit from the left hand side does not exist, and therefore we conclude that this function is not differentiable at the point x equal to 0, yet f prime of x has a limit at x equal to 0. And this is why we cannot rely in principle on the derivative at a point, at any other point except apart from the point we wish to calculate the derivative. In order to calculate the derivative at this particular point by taking the limit, we have to make sure first that f prime is continuous at that point. In fact, in this example here, we find that the derivative of f prime exists, that f prime, the limit of f prime exists at x equal to 0, and f prime 0, the derivative at 0 does not exist. You can have also a situation, the converse situation. In other words, you can have a function of this sort in which the derivative exists at the point 0. If you take the derivative at the point x equal to 0, which is this limit here, you find that the derivative is equal to 0. Yet the function itself, f prime, is not continuous at x equal to 0. Why? Because when you calculate f prime of x, you will find it in this form. This form, in fact, we know that the cosine is not has no limit when x tends to 0. And in fact, so f prime of x has no limit at x equal to 0. And therefore, since f prime of x has no limit, yet f prime of 0 exists, therefore f prime is not continuous, and we cannot rely again on the derivative at any point x, and then we take the limit when x tends to 0. So now, in fact, we can have some results. The results that we have reached so far are the following. First of all, if f is continuous at a, is it differentiable at a? No. Like, for example, modulus x. It is continuous at 0, but not differentiable at 0. Second question. If f is differentiable at a, is it continuous at a? Yes. If it is differentiable, therefore it is continuous. If f is differentiable at a, then does the limit of f of x exist? Yes, because if it is differentiable, then it is continuous, then the limit exists at the point a. If f is differentiable at a, is f prime continuous at a? No. like just the very previous example. F prime was not continuous at A, and yet F is differentiable at A. Finally, if limit of F prime at A exists, is F differentiable at A? No, this is like the previous, the one before the previous example, the one, not the last one, the one before, in which limit of F prime exists at A, yet F is not differentiable at A. Now we speak of differentiability on intervals. Sometimes, like for example, taking the limit, sometimes we found that the function may be, for example, defined over a closed interval from A to B only. And it is undefined outside this interval. Does this function has a derivative at the point A? That is a remarkable question, in fact. The interest comes here is that the function actually may have a half tangent. Yes, we cannot draw the tangent from the left-hand side of A, but we can draw what we call a half tangent. So in fact, this function here, it is defined on the closed interval AB, and it is called differentiable on the closed interval AB if it is differentiable on the open interval first AB, and the limits from the right-hand side of A and from the left-hand side of B exist. If these limits exist at A and B, from the right at A and from the left at B, and it is already differentiable in the open interval AB, then we say that this function is differentiable on the closed interval AB. Of course, these differentiable laws, now there are some differentiable laws, the students know them by heart. The derivative of the sum of two functions is equal to the sum of the derivative, product, the derivative of quotient of two functions, this is all known. The derivative of the basic functions also are known. If you wish to calculate the derivative of sine x, all you have to do, take the limit when h tends to 0 of sine x plus h minus sine x by h, and you expand sine x plus x in this form, sine x cosine plus cosine sine minus x, and then you distribute the limit. You find out that this limit is 0. This is we found in the lecture before. The last one in the limit lecture, we found that this limit is 1 and this limit is 0, so you end up with what? With cosine x, and therefore the derivative of the sine is cosine. This is quite known. The derivative of x to the n, of course, you can show that is equal to n x to the n minus 1 of a to the epsilon x. This here again the sine is the cosine is minus sine. Etc. The derivative of tan is sec square, cosec, etc. You will find that it alternates in sign. In other words, positive, negative, whereas if you wish to get the derivative of hyperbolic functions, you will find that the first three are positive. They look exactly similar to the derivative of trigonometric functions, except that you add up here an h. And then the remaining three are all negative. And now we come to the notion of differentials. What are differentials? In fact, they were introduced by Leibniz, but the scientists were skeptical about it for centuries because of the idea of what is the meaning of infinitesimally small and whether dx and dy exist, etc. But this is not important. The important thing, as Euler said, that it functions properly and perfectly. You can use it actually for deriving any derivative of any function. And I myself have tried it on even, for example, a function like x to the x. It works very nicely. And these differentials, in fact, you have the property is that they were able, these differentials were, you are able to transform your calculus which all belongs and rely upon limits, you can transform it into algebra. Look at what happens here, for example. dy by dx is equal to dy by dz times dz per du times du by dx. So if you cancel out dz and du from the numerator and denominator, you capture again your dy by dx. And dy by dx is equal to 1 or divided by dx by dy. Look at the simplicity of using differentials. Here, same thing. You multiply d by d to the power n minus 1 to obtain dny, whereas here dx times dx to the power n minus 1, you obtain dx to the power n. And the same thing, it's d by dx to the power n. And in fact, students, for example, they say that dy by dx it's equal to 1 divided by dx by dy, whereas d2y by dx square it's not equal to 1 or d2x by dy square. by dy square. Indeed, it isn't. Why? Because they are not the same. This d to y is equal to d of dy. Whereas dx square is not d of dx, but it is dx to the square. So in fact, if you want to write it as 1 over dx to the square over, if it exists, of course, divided by d to y, then actually this is it. Of course, this may not exist, but the idea is that differentials were able to transform the subject, as Bernoulli have stated once, and same thing with Leibniz, into only algebra. And for example, suppose you want to calculate d of xy, differential of xy. What you do is that you insert dx and dy with x, and you subtract the xy to obtain d of xy, and you end up with this. And then you apply what is called the neglection principle. Neglection principle relies upon something. When you see the x and dy, product dy, you neglect it. So you obtain this formula here. Suppose you wish to obtain d by dt of dxy. Same thing, you divide here by dt. In other words, since d of xy is equal to x dy plus y dx, if you divide by dt, you end up with what? You end up with x dy by dt plus y dx by dt, etc. So in fact, this is very simple. For example, suppose you want to calculate dy by dx of x times e to the power cosine x. All you have to do is that you add up with x dx, and same thing here, and you subtract x y plus dy minus y to end up with this formula here, and then you do an approximation. You know very well that e to the minus sine x1 sine dx when x is small is equal to dx, whereas cosine dx when x is small is equal to 1. So you end up cancelling terms and to finally, and this is actually the approximation that you do. Finally, you end up with minus sine x dx, which is equal to 1 minus sine x dx, and you end up with a formula like this. This is the formula that you finally obtain. And if you wish to calculate dy by dx, which is the derivative, it's simply equal to the product of 1 minus x sine x times e to the cosine x. In fact, I thought Leibniz was wrong in calculating derivatives through this way, but actually I tried to calculate the derivative of x to the x. Would this be possible through the differentials? Yes, indeed. This is what actually, because it takes a long time, this is the thing, the result which I obtained. Of course, it takes a long procedure, but it's better than taking the limit. The limit is impossible. But if you do it this way, all you have to do is you write x to the x, you write it as e to the ln x times x, and same thing with x to this power, and you end up with the formula like this, and then you do some approximations. The approximations is e to the ln x plus dx, e to the ln x, you add up dx, and then you realize that this is equal to ln x times x dx over x, and e to the ln x, this is equal to what? This is equal to e to the ln x times e to the 1 plus dx. But e to the 1 plus dx over x is no more than 1 plus dx over x, the expansion of the exponential. And if you follow the same course here, you end up with this formula here. And actually, this is differential y. So if you want dy by dx, you end up with this complicated formula. But in fact, you have succeeded. You have succeeded in using differentials even for the most complicated functions in order to obtain this derivative. And that's it if you wish to try it yourself. With the end of this lecture, what we have actually discussed here, we discussed the differentiability of function, and we said the function is differentiable if the limit exists of delta y by delta t. We said that in order to calculate this derivative, you should not calculate it at some other points and take the limit, because f dash has to be continuous. We took some examples in which the function is continuous but not differentiable, and we stated that if the function is differentiable, then it must be continuous. And then we applied this we discussed the calculus of differentials, which is actually was introduced by Leibniz, and we saw how flexible it is in calculating derivatives of most of the functions, even the most complicated ones. Finally, at the end, I wish to remind you that this lecture is also, like the previous one, is also uploaded to the site of the MEDNET2 project administered by Consortium Nettuno for distance learning. And I wish to thank you for your attention, and until we meet again, I thank you very much.